Alright folks, last video of AP Physics 1. Let's jump into these three problems. Water flowing through a pipe can fill a bathtub in 5 minutes. What is the speed of the water in the pipe? So this one is an application of the continuity equation. So volumetric flow is Q. So I'm just going to set up the general idea that the volumetric flow through the pipe is equal to the volumetric flow into the bathtub. That we can think of like the bathtub as like a very large diameter pipe, where the opening of the bathtub is there. So what that means is the area of the pipe times the velocity through the pipe is equal to the area of the bathtub times the velocity of the bathtub. And it doesn't yet look like we're going to be able to do anything. So I want to do the pipe stuff first. The pipe is a circular cross-section, right? It has a radius, so it's a circle, it's a cylinder. The cross-sectional area is going to be pi r squared, and then the speed through the pipe. So that's like normal. There's no surprise there. The surprising part comes with the bathtub itself. So I'm going to keep the area of the bathtub, but I want to recognize that when something is flowing, the way that we're going to work with it, it's flowing at a constant speed. And so the speed is just going to be the distance that it travels in a certain amount of time. And so that is going to do something kind of interesting, because if you take an area, that's meters squared, and multiply it by a distance, so if you imagine you take a rectangle and you move it through space, you've now made a rectangular solid. Well, that means that the cross-sectional area of the pipe times the velocity traveling through the pipe is equal to the volume of the bathtub divided by the time it takes to fill the bathtub. That might actually be a really easy idea because we are talking about the volumetric flow rate, which is always meters cubed per time, so volume per second. And so you can just make that translation, but you can also derive it by remembering that speed, if it's constant speed, is just displacement over time. And now I can plug everything in. So pi times 0.01 squared times the speed through the pipe is equal to 0.3 cubic meters divided by 5 minutes. Well, 5 minutes is going to be 5 times 60, or 300 seconds. And so if I were to work all that out, the speed of the fluid flowing through the pipe is going to be about 3.2 meters per second. So this continuity flow equation, most of the problems are simpler than this, that just deal with changing diameters. You might have to look up a formula for area, but there are definitely problems that involve filling a volume. And so this volumetric flow rate can always be written as either cross-sectional area times speed or volume per time. Okay. Next two problems deal with Bernoulli and maybe some more. The question here is, what is the pressure in the fluid at the right end of the pipe? We have a similar picture to the last video. We have the pressure at the bottom, which is 200 kilopascals. We have the speed at the bottom and the top, and we have the distance between the bottom and the top. So we're going to use the Bernoulli equation. So P1 plus rho g y1 plus 1/2 rho v1 squared equals P2 plus rho g y2 plus 1/2 rho v2 squared. And before I start plugging anything in, the middle of the bottom pipe is at the 0 line. And so I'm going to cancel that term out, and now I'm going to start plugging things in. I have everything I need, so I'm really just going to have to put numbers in the right spot. 200 kilopascals is 200,000 pascals. So we always convert to pascals unless we have a good reason not to. Plus 1/2 the density of the fluid. This is 900 times the speed squared. So 2 squared. That's equal to P2 plus rho gy2, so that's 900 times 10 times 10 again, and then 1/2 rho v squared, 1/2 times 900 times 3 squared. So there's a lot happening in that line, and so I'm just going to like calculate things out and then do subtraction. On the left hand side we have 201,800 pascals, and on the right hand side we have P2 plus 94,050 pascals. So that means that P2 is equal to 107,750 pascals, which is 107.75 kilopascals. So you might have to convert units, but the pascals to kilopascals is pretty easy. All right, last problem is the most involved, and I chose it because it has a couple things that I would add on to the previous video. This looks like a pair of pants, I understand. But the water is flowing through the left end, and then it splits into two smaller pipes that each have the same diameter. And so the question is like, what is the gauge pressure in one of the small sections? So it's 50 kilopascals here, and then we're wondering what it is there. Now, because these two pipes essentially have the same conditions, the pressure is going to be the same in them. So I'm not going to need to worry about like separate pressures. So what I need to do, since I don't know what the flow rate is through these smaller pipes, is I need to use the continuity equation to figure that out. But in the other video, you've never seen a situation like that. And the way that you work with it is the initial and final, but you have to keep the number of pipes accurate. So A1V1 is going to be right here. We also have a second and a third pipe, so A2V2 plus A3V3. So one flow becomes two flows, and so I would add those two flow rates together because they would have to be the same total as the initial one. Now all of these are cylinders, so the cross-sectional area is going to be pi r squared. So pi times 0.015 squared times 2 equals, and then I am going to put the areas in again for the second one. So pi r squared, this is a 1 centimeter diameter, so it's going to be 0.005 squared times V2, and then pi times 0.005 squared times V3. I also want to recognize that V2 and V3 are the same. Maybe I'll just call that VF for now. Because they have the same conditions, they will have the same final speed, and so V final is going to be 9 meters per second. So before I get to Bernoulli, I have to work with that to figure out that speed. So it's significantly larger because I had a drastic reduction in radius. So now I can use Bernoulli, and I will now write out this equation again. It's a big one, but all of the parts are important. So PG2 1/2 rho V2 squared. Okay, so in the problem it says that everything is at constant elevation. So I am going to cancel rho gy1 and rho gy2 because they have to be the same because they're at a constant elevation. And now I can plug in my variables. So 50 kPa, that's 50,000 pascals, plus 1/2 times the density of water times 2 squared. That is equal to the gauge pressure, and the pressure is going to be the same no matter what because they're in the same conditions. And it's going to be plus 1/2 times 1,000 times 9 squared. On the left-hand side, I would have 52,000 pascals. On the right side, I would have P2 plus 40,500. And so P2 is 11,500 pascals, or 11.5 kPa. And there you have it. That's your last problem. And now go forth and do some of your own practice. Thank you.